Rafael, Chavez, Professor Behrens. This is my lab report. Introduction to the lab. So, the purpose of my lab is to observe and improve our understanding of magnetic fields and bar magnets through creating a visual representation of our lab which observes the relationship between distance and magnetic field, and to use the distance dependence of magnetic fields and likewise the Biot-Savart law to identify the magnetic moment of the bar magnet. Similarly, the magnetic field of the bar magnet using GlowScript Python. Compared the measured magnetic fields to the simulated magnetic fields also. Involves some fundamental physical principles of the lab. Using a bar magnet to observe and model the magnetic dipole, we have the Biot-Savart law, the distance dependence formula of the bar magnet, and the relation between the magnetic moment and a constant k, distance from the bar magnet for a specific magnitude of the field, the distance r, and a value n. A brief preview of the main lab results. The magnetic dipole moment U is 1.4875 amperes per meter squared. The n value of the graph, so all the constants together, is 2.771. Our off-axis magnetic field is measured to be 7.47 times 10 to the negative 4. The stimulated one is 2.771 times 10 to the negative 4. And this big difference is due to different errors that we're going to talk about later slide. The magnitude of the net magnetic field is inversely proportional with the observation location of the magnetic field. Main physics ideas. The Biot-Savart law, which relates the magnetic field to produced by an object at an observation point to the current I running through an object, and then the distance between the source of the field and the observation point. The direction of an on-axis magnetic field is the same direction as the magnetic dipole moment. It is also the same direction as a conventional current I running through the dipole. Reasoning for using specific models and assumptions. I assumed the bar magnet to be a magnetic dipole so I could use the Biot-Savart law equation for calculating the magnetic field of a dipole for the experiment. We assumed that the phone magnometer to be aligned orthogonally with the magnetic pole of the Earth as well as to eliminate the magnetic field contribution of the Earth in our measured magnetic field by the magnometer. Initial conditions of the lab, we have the bar magnet, the magnometer on the phone, and the ruler. Details of the experiment. First, location of the magnometer on the phone was pinpointed by sliding the phone perpendicular on the ruler, both vertically and then rotated horizontally in relation to the ruler, and slid along the ruler for the rest of the lab at different points for specific net magnetic field contributions that we were looking for. Data analysis and results. We have the graph right here for all our data. We have the different distances where we measured to the specific field, and then we have the averages of those magnetic fields in the bottom and average distance, and then we have our net magnetic field that we calculated for it that's created by the bar magnet below. Details of the coding. So here we just have the code that creates our magnet at the origin. Then we have our magnetic field, magnitude of the magnetic moment created by the bar magnet here that we had defined. We have our constant up there. Then we have the function that creates our dipole for the Biot-Savart law and returns it, our B scale, and our distance from the point. Then we have the B scale distance, but we have all these arrows that represent the different magnetic fields, and then we have more arrows for that are going to be represented in our visualization. More arrows are being represented by our visualization, and then down here we have also more things for our visualization, which is right here. Yeah. Possible sources of errors. Nearby electrical equipment can also contribute to the net magnetic field observed by the magnometer. So computers, lights, etc. could be contributed and amplify the net magnitude of the electric field measured by the magnometer. Accidentally moving or bumping the smartphone could result in inconsistencies in the measured magnetic field by the magnometer or distance. Could also mess up the orthogonality of the phone's magnometer to the magnetic field contributed by the Earth that eliminates the magnetic field. Yeah. And then failing to line up with north before starting, the X and Y components of the Earth's magnetic field will contribute to the measured net electric field, thus resulting in inconsistencies from the measured and the actual magnetic field of the bar magnet. Still, iron objects near the smartphone, they could be polarized and then impact the net magnetic field of the system, contributing and amplifying the measured net magnetic field. What ifs? So, what if you hadn't oriented your experiment to compensate for the Earth's magnetic north, had laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results change? The measured magnetic field would be different due to not counting for the magnetic north. The X components would be different because the magnetic north would contribute to the magnetic field measurements, and the Y components would also be different due to not counting for the magnetic north. And an intermediate angle magnetic north would contribute to both the X and Y components of the magnetic field. Because we lay the magnometer on a flat surface, the z component would not change. It would not see a negligible change. What if you were to stick two identical magnets together end to end and run the experiment again? So the magnetic field would increase and be doubled at any given point compared to the previous run. There would also be a new magnitude of the magnetic field approximately double from the magnetic field of one magnet, due to the property of superposition, which would be proven experimentally. And the measured distances of each magnetic field threshold of the value would decrease due to the increased magnetic field from the two magnets. Thank you for listening.